Hi there. So we have this another circuit about current reference and the voltage reference. So let us analyze this. So what you see here, we have this power supply V plus connected at these nodes. Then I'm using the resistor R to let the current flow. Let's call it my I reference or I in flowing through the resistor R. Now I have used transistor Q1 and Q2 here. The pin collector and the base of transistor Q1 are shorted together, making that transistor a diode connected transistor. Is diode connected transistor. So it is simply a PN junction when I have such kind of arrangement. And now, all right. So when we say it is diode connected, it's a PN junction and it has characteristics like IB versus VBE, right? And this is how you actually uh, your circuit current in the transistor Q1 and will vary. It has an exponential relationship with the base emitter voltage. Now we said that the Q1 and Q2 are exactly same. It means their beta value DC current gains are same. Their IC max and VCEO ratings are same. Okay, VCEO2. This is one, IC max 1 and IC max 2, right? They are equal and so they are from the same manufacturer, same type. So if I use 2 and double 2, double 2, this Q1 and Q2 both are of the same value, same type. And now the value of the reference current that I'm generating using the resistance R can be given as V plus minus VBE. This is nothing but VCE also because of the diode connected transistor divided by the value of resistor R. So choose appropriate value of resistor for a given voltage V plus. VBE is fixed. For a silicon diode, it is about 0.7 volt and you will have the value of reference set. Now, like I said, Q1 and Q2 are equal and here their VBE1 and VBE2. VBE1 is equal to VBE2. So here basically because of the input current I reference, I'm generating this voltage VBE, right? And that is equal to, that is helping me to bias this transistor Q2. But wait, we have the addition of the resistor here. So it won't be equal to VB1 is not equal to VB2. If there is no RE, then it is the case. But RE is called as emitter degeneration resistor. So is basically is helping us to offset the current gain error due to the finite base current values of transistor Q1 and Q2. See here, I reference comes and it is splitted between two parts. So one is your IC, which is here, and then this current is coming here, getting splitted again in two parts. And these values are IB1 and IB2. So there are finite values of base currents Q1 and Q2. Here, therefore, I out would not be exactly equal to I reference, rather it would be 2 times IB. Okay, so your current gain is not 1. There is some error, finite gain error due to the finite value, the gain error due to the finite values of the base current. So emitter generation resistor is added to get rid of this one so that your current can be approximated to reference current. So now the voltage that is here, which is a emitter voltage at the transistor Q2, is a drop across the voltage the resistance RE. So here your I2 flows into RE and VE2 is actually VE2 is equal to VBE1 Well, this is the voltage at the VB, not VB1. Yeah, you can say that VBE1 or VB minus this VBE. Am I right here? Just a moment. Right, so V2 equal to VB1 minus, let's say, this drop here, VBE2 minus VBE2. Yeah, so that's your VE2. So it's also equal to VC. That is basically the voltage at the collector minus VBE2. Okay, that's how you get the value of VE2 right here. And obviously, here is your collector pin or of the transistor that has a voltage VC, and then there's this drop VCE will be across the transistor Q2. And you want to make sure that in order to have IC2 is equal to IC1, that is collector current of transistor 2 equal to collector current of transistor 1. We need to make sure that your transistors Q1 and Q2 are operating in the linear mode of operation. Linear mode of operation suggests your transistor is operating here uh, to the right of this line. That's your active mode, right? And that is how you will have the operating point somewhere here for a value of collector and the value of collector to emitter voltage, right? And then now the voltage at the collector is basically helping you becomes the voltage at the base of the transistor Q3. And then here you can see that this line is shorted here. So is the transistor Q3 is collected to base bias through the resistor R actually. And that's why you have this VCB, right? And you need to ensure and make sure for a given values of voltages and the resistance, you will calculate voltages and the currents into the circuit to make sure that your transistor Q3 is biased in an active region. And finally, voltage at the collector of Q3 is your reference voltage. However, this reference is not constant if there is a change in the supply or a change in the temperature or something like that. So it is just to show you how we can generate the reference voltage by the transistors circuit. And the purpose here was to analyze this circuit. You can apply the KVL also here. You can apply the KVL in this loop, which will be V plus minus I times R. The I is the current flowing through this. Then minus VCE minus VE2 is equal to 0. And accordingly, you get the value of required quantity you want. Okay, for a given value of a resistor and a chosen value of VCE, for example, if you choose VCE to be half of the V plus, you get the value of current in this circuit, and IB2 is also here. Okay, and yeah, that's all. So put some comments in the video that you would like to say, and hit the like button if you like the videos. Stay tuned for more circuit analysis videos like this. Till then, wish you happy learning.